Hello, today I'm going to talk about running large language models for generative AI on your laptop. Desktops work fine too. What is a large language model, or LLM? It's a machine learning model that has been trained to generate text in response to input. It can generate text responses to questions, summarize and critique written material, and provide rudimentary language translation. Some models have also been trained to work with computer source code or image analysis and generation. You can typically carry on a conversation with an LLM, and it will draw from its training materials when generating a response. It does so quite well, to the point where many people anthropomorphize the model as though they were talking to a person, but it's not. If you're watching this talk, you're likely already been digging into generative AI and large language models, but I hope this perspective might help you add something to your own understanding. A bit about my background. I'm a software developer at Do It. I'm not a mathematician, but have been coding for food since the late last century. I do have a working knowledge of how all the math works, but I'm going to rely heavily on library code since I'm an application programmer and not a theoretician. My focus is to show how to get this working enough to do your own evaluation, testing, and maybe produce some ideas on what to do with it, if anything. This presentation is meant to be accessible to other application programmers. If you're an AI researcher, I'm sure you're going to have many comments, clarifications, and corrections about what I'm going to go over. I'm going to be describing how to work with generative AI the way I understand how it works to get the results I have. I'll be covering some of the freely available resources for working with LLMs locally and demonstrating some practical hands-on examples for those with at least basic JavaScript and/or Python skills, and hope to make it easier for you to start working with LLMs without paying any money whatsoever. Yes, this presentation includes AI-generated images, since I think they're cool. I'm not a great artist, and I don't have any money to pay one. Large language models have significant differences from supervised learning models. Supervised learning models have been around for a while, and are used for things like classifiers to sort fruit into different grades, detecting flaws in industrial products, categorizing written material according to sentiment, optical character recognition, and detecting faces in pictures, among others. The training in all these is similar. You create a curated data set of examples of the things you want the model to learn, such as 1,000 images of peaches, some of which are good and some are bad, and it learns to discern the good peaches from the bad ones. There's a lot of work that needs to go into creating the training data, and the training process needs to be carefully monitored so it optimizes predicting the correct answer. Is this a good peach or a bad peach? Large language models take a different approach to training. The training data is a large volume of unlabeled text. During training, the text is tokenized, and the neural net analyzes the tokens based on their relationships to each other, their prevalence, and many other properties of the text itself. It isn't taught the word dog by showing it pictures of a dog labeled dog. It learns how to use the word dog based on sentences that have the word dog in them in the training data. That's an important point that bears repeating. An LLM understands the word dog based on the words and sentences it appears in, not on real-world dogs as things. A large language model does not write, it generates text. So this is how a supervised learning model is trained. It wouldn't have to be just a dog's image. It could be blood samples or audio recordings of sounds. But in all cases, you provide it with correctly labeled samples of the data you want to learn about and test it by having it correctly labeled data it hasn't seen before. One characteristic of a supervised learning model is it can provide a degree of certainty or uncertainty it has about the answer. A large language model learns about dogs by creating a token for the word dog, along with all the other words, and then learning the patterns that they appear in, conceptually grouping them so that the mathematical distance between two tokens is related to how frequently they appeared close to each other in the training data. It is unable to determine the degree of certainty it has about the answer, since that's not its goal. It's not going to learn these things about dogs as facts. It's going to develop a model of tokens where these words appear closer together than other words. If you ask it what a dog's species is, it might very well get the right answer because it's found in the training data in the same sentence. It's this behavior that tends to lead people into thinking LLMs understand things. LLMs also demonstrate abilities that have been described as emergent, in that they demonstrate skills and knowledge in things that they weren't specifically trained in the way that a supervised learning model would be. LLMs aren't taught words the way the humans are, connecting a real-world representation of a thing to a word. They learn words as statistical tokens that have a probability of appearing at a certain place in a certain type of phrase. By consuming tokenized raw text that refer to arithmetic, the LLM can appear to understand arithmetic, meaning it returns correct answers for word problems. Sometimes. LLMs were trained on volumes of raw text that referred to Paris, so if an LLM will respond Paris to the question, what is the capital of France, since that's the most likely answer. So far, over the generations of LLMs, it seems like the larger volumes of raw text that an LLM is trained on, the more prominent the emergent abilities become. That's the theory, anyway. LLMs also have some demonstrated capabilities that look like reason. It can infer responses to requests based on other common requests in the training data. It can generalize based on linguistic patterns and tropes in the training data as well. There is likely to be a strong correlation between text describing the sun shining and text describing clear weather, so the LLM will consider these phrases close together in its model and they'll be included in the response context. It can complete the analogy shown for a similar reason. Text describing dogs and cats and text describing the sounds that animals make will be closer together in the model. Does being able to answer questions about a thing mean the same as knowing about a thing? Is predicting the likely answer to a given question the same as answering the question? All of this raises questions about the relationship of knowledge and language that I'll leave as a future late-night dorm room conversation for the viewer. It's going to be helpful to have a very basic understanding of the generative process as we go over the demos. Here's a very brief description of how an LLM converts your text input into a response. If you're an AI researcher, please be merciful in your reviews of this explanation. First step is tokenization. The system breaks down your input into words, subwords, and characters. This isn't terribly different than what most search engines like Lucene do when indexing data. In the embedding step next, the LLM converts your tokens into lists of weights or vectors based on the embedding model, which is usually associated with the LLM and its training. During the encoding step, the embeddings are fed into the LLM as input and translated to the LLM's specific weights. And then contextualization next, that's where the model takes the encoded input and pulls in related or similar lists of weights from its training data. Simplistically, this is how a model understands synonyms, positive and negative sentiments, and so on. Next, the model attempts to predict some plausible next words for the input based on the tokenized content created in the previous step. It will typically choose more than one possible word as the next word in the output. Sampling comes next. The model will pick one of the predicted next words and output it to the response. There are various ways it might do that, from a completely random choice to statistically most probable and some others. Once the next word is chosen, it's appended to the output. Then the model will iterate on the process of prediction, sampling, and output until it reaches a stop condition, such as a certain length of text. Then the list of generated word tokens is converted back into text and the output formatted as the user desired if it was specified in the input. In my mental model, tokenization and embedding happen prior to submitting the input to the model's neural net. Encoding and contextualizations are processes internal to the model that prepare the input for prediction. Then the iteration over the prediction, sampling, and output steps happens in the model's neural net before outputting to the post-processing step. And that is probably about as far deep as we need to go into this to know how to use them, but let's visualize a few things to make it even more clear. So one step at a time, tokenization splits the input up into words and symbols. Embedding is going to assign lists of numbers or weights to those word tokens. Note the actual vectors used in an embedding can be hundreds of numbers, not just 3. And these are based on an embedding model that's usually separate from the LLM, but will have some relationship to its training. The embedding weights are then given to the model. It does a similarity search to connect it with data in the neural net. And this is where it creates language context to generate the response from. This is like the groups of words and phrases that are relevant to the question because their own weights were similar. Most likely next word for the response then is chosen and added to the output so far. and after several are predicted, and then it just keeps going on that, predicting a set of next words, choosing one, appending it to the output, and then reevaluating it to predict another word until it decides it's done. So getting to the hands-on portion of the talk, Meta, aka Facebook, released their own LLM named Llama, then Llama 2, now updated to Llama 3 as an open source project. It spawned dozens of other LLMs either based on it or inspired by it. The Llama 3 model is freely downloadable, extendable with tuning, and it's available for commercial use if desired. According to Meta, it was not trained on Facebook data, but rather web scraping, GitHub source code, and Wikipedia. Mistral is another open source model. This one is from a French company named Mistral AI and carries an Apache 2.0 license. It was trained entirely from scratch on an open source data set. It does very well for its size, so this is the model I usually use myself for general experiments. As I mentioned, there are a lot of other open source LLMs available now, some entirely original, some derived. If you get bored and want to fill up a few terabytes of disk space, the huggingface.com website is currently the largest archive of freely available machine learning models out there, or at least that I have ever seen. There are specialized models that are fine-tuned with additional training data in domains like programming, image analysis, DevOps, creative writing, even medical data. Most of these models are between 2 and 30 gigabytes and have various levels of training. You'll see a notation by some models, such as 3B or 13B. This denotes how many training parameters were used during training, where B stands for billion. Typically, the larger the model, the more fluent it is, and the more resources that are needed to use it. This doesn't mean that the models with more parameters are necessarily more accurate, but it should be more creative at least. So there are numerous command line and desktop programs to run LLMs on a typical developer machine. I can run a 7B model using Ollama on a Mac with at least 16 gigabytes of RAM and an M1 chip. It's not as fast as ChatGPT, but it's not intolerably slow. I've been able to run a 13 billion model on a M1 Macbook with 32 gigabytes of RAM, but it was a little slow. You will need more RAM to run a 70B model than you will typically find in a personal computer. A rough rule of thumb is that LLMs require about 1 gigabyte of RAM for each billion parameters. So I'm going to be using the open source Ollama application to run the demos in this presentation. It's cross-platform, can provide an OpenAI-compatible API, and provide some useful model management features in a Docker-like context. It also has Ollama-specific Python and JavaScript client interfaces, in addition to being able to use the ones provided for OpenAI models like ChatGPT. Ollama is forgiving about hardware and will usually give it a try, even in minimal resources. For best results, I'd advise using a computer with at least 4 to 8 CPU cores, 8 to 32 gigabytes of RAM, and plenty of disk space. If you have a GPU or an Apple Silicon GPU, like an M1, M2, or an M3, it will greatly speed up operation. In addition to using different models, you can easily customize some basic properties used by the model. The most impactful is the system prompt, which is a preparatory prompt used by the model to frame the response. For example, most models have a fairly generic default prompt telling the LLM something to the effect of, "You are an AI assistant." And that's the voice it will use when answering you. However, when you can have some fun with that and tell it to answer questions as though it were Mario from Mario Brothers, and it'll start talking about rescuing the princess in addition to answering your questions. Or you can focus it on a certain type of topic, such as answer as an experienced DevOps developer, or answer as a high school math teacher who can explain complex topics using simple language. Or even ask it to answer you in a different language, such as French, or in a specific format, such as JSON or tabular data. The system prompt acts as sort of a tiny linguistic program in itself, in that you can greatly affect the output text based on what you tell the model you want. The other parameters have somewhat less effect on the output, but can be noticeable. The two most impactful parameters are the temperature and context window. Temperature affects how creative the model will be in response to input. This affects both the vocabulary and syntax of the output text and how likely it will be to extrapolate from the training data, as well as deviate from what your prompt requested. High values are good for creative writing. but lower temperature values help keep the LLM from being so creative with language that it just makes everything up. Context window determines how many tokens or word bits that the model can deal with at once. It's limited by the specifics of the model you're using, but it determines how much information the LLM can include in its generative process at once. It's analogous to its short-term memory, but only for the lifetime of the request. Most of the rest of the parameters available affect smaller parts of the algorithm, and mostly about word choice. Ollama lets you create easily customized copies of existing models with pre-tuned parameters and customized system prompts, again, using a Docker-like file called a model file. You will have fewer reasons to do that once you try out the code I'm going to demonstrate, which will let you set those on the fly. But if you find it convenient to create a specific customization for reuse, this works well. Ollama model files are heavily inspired by Docker files. You declare the existing LLM you are using you are basing your new version on, and set some parameters in a new default system prompt, and then you can tell Ollama to create the new model using the new parameters. It will still be the same trained data model internally, but the default behavior will change. All right, let's get to the demos. All of the example code I'm going to talk about is available on both DoIT's GitLab instance and on GitHub. So if you're following along at home, this would probably be a good time to clone the repo locally so that you can try them out yourself. Also, you'll need some models to work with, so once you've installed Ollama on your computer, you should pull the models we'll be using using the Ollama command line tool, using the commands on the screen. The easiest way to test out Ollama is to just run a model in a shell session and enter your prompt. This isn't a bad idea to do periodically anyway to make sure it's still working. Ollama tends to update itself in the background, and I've periodically had to restart it to get it working again. One thing to be aware of when you're running it in the shell is that the Ollama application itself is managing your chat history when you use it interactively, so as soon as you end the session, it'll forget what you've talked about. Okay, the first thing we're going to go over is just how to use the Ollama program right in the terminal. It's a lot like Docker, like I mentioned, so we can list the large language models I've already downloaded with Ollama list. Got a few, so let's run one. And it's going to queue that up, and we're ready to go. I'm just going to ask it a question, and I want you to see how quickly it generates the answer, and you can see it coming out word by word as we've been discussing. And that's faster than I can read, so speed looks good. And, well, I didn't check the wavelength, but it is a reasonable looking answer, like most of them. So in addition to setting the role or voice of the response and request-specific formatting, prompts can take advantage of in-context learning. That's where you can provide information in the system prompt that the LLM can use while generating the response. We'll be going over something in a bit that makes extensive use of this. You can also provide the LLM simple instructions for it to follow while generating the response, such as a series of steps. Hopefully you can copy this from the PDF with the slides, if you're interested, but it's an 811-word prompt that will request the LLM act as a second edition AD&D Dungeon Master and play a game of D&D with you. It's quite detailed, but unfortunately it's so long, it doesn't leave most LLMs with much context space left to remember more than the last few turns of your game. Works a bit better on ChatGPT since it has a much larger context window. So, Ollama provides an OpenAI, aka ChatGPT, compatible API. So you can send a prompt request to a model using the REST API, and then later switch it to ChatGPT if you want. You can set most of the parameters as well as set the system prompt and manage chat history using any REST client. Note with this prompt, which we'll go over, we didn't actually ask it to do anything. We gave it a role in the beginning of a sentence, and the model generated the next likely words, which were a story. So let's try it. Okay, now we're going to show you how to just use the OpenAPI compatible API with curl, real simply. What we're showing here is a format of a request that we're going to send to Ollama. That's almost exactly the same as you'd use with ChatGPT. We can set the model, change it for every question if we want. We're going to set up a system prompt, giving it a role, and then give it some input text to work with. And we're just going to start it with once upon a time ... and see if it goes from there. And so this is going to wait until the results are completely done before it sends it back, because we're not doing streaming right here. And so it's off crunching numbers, generating words, and we're done. And it generated a story. And here we have Once Upon a Time in a Far Off Land. Yeah, it's on a dark and stormy night. It's going to be full of stereotypes and tropes. And, this isn't literature, but there's your fairy tale, completely original, but made from pieces of every other fairy tale it's ever seen. One thing to note here at the bottom in your API response, you get an output of how many tokens are currently in the context, or that how many tokens were used in that request. And this response here of, I don't know how many lines that is, but it used up 504 tokens or word parts, and that's about a quarter of the length or the quarter of the size of a typical context window for something running on your desktop is 2048. Certainly there are much larger ones available online if you want to pay for it. ChatGPT, it's huge. I don't even know what they're up to. It's in thousands and thousands of tokens. Maybe 100,000 now, the new one will be. But that gives you an idea of how to use the API. And since it's just a REST API, you could call that from literally anything that could do REST, which is almost everything. Moving on to using code to do this, we'll try using JavaScript to set up a simple REPL shell so that you can carry on a conversation with the model using the API. All right, now I'm going to show you how to use that REST API from within JavaScript, a Node app here. And we'll go over some things that can show us that are easier to see this way. At the top, we're just going to set up a little REPL shell, which is sort of like terminal-based chat, where it just asks for input and returns the answer in a terminal. Here we have our model options. We talked about these a little bit before. There's temperature, you can set a context window. And again, most of these have to do with word choice. If depending on what you're doing, you might find luck tinkering with those or not. Lastly, here I have seed, which is commented out, and I wanted to show you that it was possible. There's random number generators, of course, inside this process, but if you give it the same seed every time, you will get the same answer. So it is one way to get a repeatable answer with this technology. So here's this process input function. Down here below, you can see we're calling that every time the user hits return in the terminal. So that's what's going to handle our input. At the top here, we're just formatting the same API type request we did before, sending it to the URL that Olam is running at, and then we'll get the answer back. So I'm going to show you a couple different system prompts here with the same question, so you can get an idea of the effect of that on the response. So let me get into the right terminal window. Now I've already made sure that I was running the right version of Node. I'm not. Okay, so do I have NVM loaded? Use 18. Yeah, I do. NVM is handy, by the way, if you got a bunch of different versions of Node running around. You can set the current one in the terminal session and stuff and switch between them. So now I'm running Node 18. And I've already run npm install. I'm not going to make you watch the output of that, but suffice it to say it installs a bunch of libraries. And then to run it, we're going to go node main.js. It's going to queue up something that asks for a prompt. And we're going to ask it the same question we did before. What is blue? Now, the way this is written right now, it's also going to wait until the answer is completely generated before it returns. So if it were a longer answer, we would have waited longer. But there it is. That's very similar to the other answer we got. That's using the generic, you are a helpful assistant. Now, let's change up a little bit and say, how would a poet answer that question? And we're gonna change the system prompt to "You are a poet," and then we're gonna ask it the same question: is blue? And what we get back should be more poetic. And look at all that. It was just kind of going on about it. Blue, my dear friend, is a hue, a tone, a shade of color in the. Yeah, okay. It's poetic anyway. It's doing it. So one other one I found kind of fun. Actually, a couple here. You are a shaman, right? That's a weird point of view to have to ask this question. So what do they think about what is blue? And yeah, it's telling you what the blue means to their shamanic beliefs, which are currently undefined. I didn't actually ask what type of shaman it was, but apparently it has a belief system. And you see, it's copying answers from other texts, obviously, but that's how it changes the voice of that. So you can see the effect there that a system prompt will have on the generation. And wanted to go over one more thing. Get this running again, back to the helpful assistant one. Clear the screen, and I'm going to say, remember this word, orange. And it will assure me I will remember the word orange for our current conversation. But then say, what word did I ask you to remember? And it's got nothing. It doesn't remember me asking it to remember a word. There's a very good reason for that, and we're about to go into that. As you notice in the example, it can't remember anything. It can't remember things you just said to it or what it may have said a few responses earlier. That's because LLMs are basically stateless. They don't have a built-in memory of past requests. You have to implement one yourself by using a message history list. This is also the only reason more than one person can use the same LLM at once. It's the list of questions and responses from the chat so far, the message history list, starting with the initial system prompt and ending with the current question. You submit this entire list of questions and responses to the LLM with every new question, and it will remember your whole conversation up to there because you're basically recounting the whole thing to it. So we're going to show you an example like the last one, but we're going to implement a chat message history. You can ask it to remember something, and it should be able to use that in a response later in the conversation. So here's more or less the same chat program, but we're going to implement message history list, so it'll have a memory to work with when we have a conversation. We're going to, as before, set up the REPL shell, and then we're going to create a message history list right here. It'll start with just the system prompt in it, and we'll be adding to it all the inputs we send and all the responses we get back. We'll be appending those to this list for every request. It's a process input function, similar to before. It runs every time the user hits return, along with what they typed. And then first step, we're going to take the input string the user just typed and pop it into the message list. And we're going to set up our request as before, a little simpler. We're not going to add a bunch of options we aren't going to use anyway. And messages, we're going to include our current message list at the time of the question, and just keep sending that along every time we send a request. I added a calculate tokens function so we can keep an eye on how many tokens the entire message list is using, since there is a limit, as I've mentioned, of the context window. And the rest is, again, similar to before. We're going to push the response we get back onto our message history list, calculate the tokens, and then ask for more input. So let's run it in the shell, and see what we get. Let's start by trying the same test. The other one failed. So remember this word, orange. I will ask you for it later. It's 22 tokens, and it's promising to remember the word. And it says it's okay if I don't ask for it later, too, so that's fine. Oh, good. So now let me ask another question in between. What is blue? And that's similar to before. And then I'm going to say, what word did I ask you to remember? And it remembered that I asked it to remember the word orange. And it has thoughts about orange. So you can see, basically with every question, and for that last question, we sent it all of this text that we had exchanged with it before. So it isn't really a memory as much as it's a lookup list or message history. And that's how it remembers things. Okay, next, we're going to add a web interface, which allows on-the-fly replacement of the system prompt and uses streaming output, so you'll be able to see the response appear on the screen as the neural net predicts the next word. You can clear the chat history when you want to start over. All right, now we're going to start doing some things in a web browser. It'll be a little prettier to look at. The next examples are going to all be in Python. Python has a lot of tools for working with machine learning and that sort of thing. And a lot of it gets to be a little easier this way. So what this is going to do is we're going to create kind of a chat GPT lookalike. It'll run in a web browser in the same way, and it'll have a chat history. We're going to use the stock OpenAI Python client, which is released by ChatGPT. If we were going to use this with ChatGPT, all we'd have to do is not include the base URL, which is sort of an override where we're sending it to Ollama. And we would have to put in our valid API key that we get with our paid OpenAPI ChatGPT account, or OpenAI rather. But why would we do that when we have Ollama running for free on our desktop? So that's what we're going to use. Here's our base prompt. Basically, you are a helpful assistant. I see a lot of people suggest you try to give it guidance to only respond with answers that you can verify from the training data. I don't know how much that helps, but we're going to include it in there anyway to cut down the confabulation. Predict, we're using a web framework called Gradio, by the way, for this. And it's sort of, it does really well with machine learning tasks, displaying numbers. It's kind of designed for that. This is going to be running down here in a purpose-built chat interface. It was canned. It was already built in. And every time the person pushes a return in the input box, it's going to call this this function. This is similar, I guess, to the process input from the JavaScript code we were looking at earlier. First step, we're going to pass the history list from execution to execution here in this variable. Gradio is going to hand that to us, because this is actually also what is displayed in the chat history on the screen. It's taking care of laying it out and all that. We only need to give it something in a format that it understands, which is this history list sort of thing here. We're going to start again with the system prompt. Then we're going to rebuild the list from what Gradio gave us into that same format, message by message. And then we're going to append the latest request in that the user just typed, and pass it all to the Python client function to send it to Ollama. A lot of the same settings as before. Model is Mistral. Here's our messages, setting the temperature. This is different. It's able to do streaming format, and what that's going to do is it's going to send us a response every time that it generates a word. So we won't have to wait until the end to see the answers. And what we'll do is, while we're iterating over what it hands us back, which is kind of an object that can pull the streaming answers in, we're just going to append it to the response text. And you'll see these yield statements here. What this does is it just forces Gradio to paint this to the screen. This is what the text response will be in, and we're just going to force it to do that. And then when all the response is done, we're going to make sure we return the whole one at the very end. And so now we can just, let's launch that and give it a try. I have to get my browser over here. And that'll run on our local port. Let me pull that over here. Here it is. And let's ask it some questions. We'll start with this. One other widget I put on here is we can set the system prompt on the fly, so we can try a few of them out that way here. So let's start with what is blue, same as we did before. Yeah, I should make the text bigger. And same type of answer. So let's change the system prompt to "You are a poet in the style of Lord Byron." I have no idea what this is going to look like, but let's try it. What is blue, Lord Byron? Yeah, it's got that down, doesn't it? All right, so you can see that. One thing you can do that's handy in here, you can retry, and it'll basically run the same input again. It's a little long-winded as Lord Byron, I note. You can clear the input and start again. And there you go. There's your ChatGPT clone running on your desktop. So this is great. You have a little Oracle of Delphi running locally on your computer, all ready to get answers to all your questions. It was easy. What could go wrong? Well, it's not that an LLM can't answer a question correctly, because it can. It's just that factual correctness isn't the goal of the math. The models are trained on how words are used and how they relate to each other. When it doesn't know the answer to a question, it doesn't know that it doesn't know. It just keeps generating plausible next words until the stop condition. It doesn't write, it generates text. How can we address that? Well, one way is to add additional tuning to an existing model, a process referred to as fine-tuning. This is often done to add specific domains of knowledge to a model, such as programming. It's a resource-intensive process and not as accurate as one would hope. By providing it with samples of text that includes the specific knowledge, it becomes a little bit more like supervised learning in the sense that you are curating a data set for it to learn from, but the outcome is different. The tokens from the new data are added to the existing tokens from the base model, so the result can be slightly unpredictable. In the end, the goal of the algorithm is still to predict the next word, generating the most likely answer, but not necessarily the correct answer to a question. There's another way we can improve the quality of answers, as well as provide our own data to the model to enable it to discuss the information in it. It relies on the ability of LLMs to answer questions based on a provided context. It uses in-context learning to construct a response based on the information you provided with the prompt. You can provide it with text of your employee manual and request that the LLM limit its response to the information you provided. Of course, if you recall the context window I mentioned earlier, there's a limit to how much information the LLM can keep in the generation context at once. Again, for most models you can run on a laptop, the limit is either 2048 or 4096 tokens. So since your employee manual is likely longer than that, you might need to limit the context to just the information that might be relevant to the answer. One way to manage this is to pre-tokenize the data you want to include and store it in something like a vector database. Then use a retriever component of some sort to fetch the relevant tokens from the database based on the question. This brings the well-developed science of information retrieval into the generation process so that the LLM is used more as a summarizer of the context you provide. Typically, you would use a special system prompt when using a retrieved context that tells the LLM to only use the provided information when generating the response. I would note that telling the LLM to only draw from the provided context is more of a guideline than a rule. It still may confabulate things from outside the context, but this helps, as this and keeping the temperature low. So once your answer data set is tokenized and stored, you can use a retriever to fetch the relevant tokens based on the tokenized question the user asked, and then pass all of that to the LLM to generate the answer. So here I'm going to demonstrate a simpler form of the same idea, where we tokenize a small set of web pages and then ask the LLM questions from the material. All right, this is going to be an example of retrieval augmented generation, also using the Gradio library in Python as before. This process input line function is kind of similar to the last one. This is called every time a user hits the return and sends us something. This will get called with their input. We're going to use the chat Ollama class for this one. It comes from the LangChain libraries. LangChain is a set of extensive set of libraries, Python libraries, and JavaScript libraries now that are sort of purpose-built and designed to work with machine learning and LLMs in particular. A lot of different tools in there, from chat APIs to tokenization and so on. Then we're going to set the temperature to 0, and I found that helpful with this sort of task because we don't want it to be creative. We really only want it to pull from the context. And I don't even care if it's repetitive as long as it's the correct answer. That's fine. We're going to try and cache this retriever we're going to build that's going to handle the tokenized data from the URLs we're going to look up because it takes a little bit to build. We'll split the user's URL list up into a list and feed each item to this web base loader component from LangChain, which is going to pull the web page in and grab the text from it. And we're ultimately going to create a list of documents. And then we're going to split that up into chunks that overlap a little so we don't miss any words. And sort of cut it up into pieces that the LLM can deal with, and then store that in a Chroma RAM-based vector store. This could just as well be Elasticsearch, just any vector store could be used here. Similar types of API. There is an Elasticsearch component that can be used. And we're also going to give it the embedding model to use to store the text. And that's going to convert it into numbers. And finally, we're going to ask it to give us a retriever component that the LLM can use to pull data out of that vector store. The prompt we're going to use, we kind of went over, answer the question based only on the following context. This context is where we're going to put the retrieved data that the retriever returns for our question. And then we're going to ask the question, and then here's the LangChain chain. It's the way you work with tasks like this in LangChain is sort of streaming. You pipe it from one function to another. It's kind of uniform that way, easy to work with. And then at the very end, we're going to submit it all to the model and return the answer. So first, let's activate our virtual environment. So we get all the libraries loaded. I already installed everything in the requirements file. There's instructions in the GitLab repo or for how to do that. It's a standard list of the libraries it uses. You can install that with pip install. And I won't do it now because it takes a minute. So let's having already done it, let's run the application. There it is. All right. So let's try. I was looking around for some good URLs to use. And it was working best with something that was a FAQ format, kind of flat, and that was the Google Workspace FAQ. So we're going to pull that in. What that page actually looks like is it does have all the answers in here. They're all folded inside little CSS chunks. The web loader doesn't have any problem with that. It's able to get to the data inside there just fine. So we're going to pull that in, and then we're going to ask it, can I store PHI in Google Workspace? And see if it has an answer for us. And we can see down here, it's working on rebuilding the database, and now it's submitting it to the model. And it's thinking, and there we go. According to Google, they comply with various standards, but it's not HIPAA compliant, and if we need to store process PHI, we have to get a BAA. I know all that's true because I've done it before, and that is exactly how you do it. So would I trust it for any answer like this? I don't think so yet, but it is possible to keep it fairly close to the truth if you need to. Next is a similar example where we tokenize a document, then ask an LLM questions about it. For this one, we'll use the Llama Index library, which is designed to make the implementation of retrieval augmented generation systems much easier. I left the UI off this example so that it was clear how little code was involved in getting the RAG process going. And so here's the demo. Now we're going to do a similar task using the Llama Index library. This one isn't really going to have a user interface or anything, so I wanted to show you how little code is required to do what we did in the last retrieval augmented generation demo. So Llama Index is really purpose-built for doing RAG type generation, and makes it pretty easy. First step, we're going to load in a directory of text documents, and all I have in there is the entire text of Mary Shelley's Frankenstein. The whole story is there, and we're going to ask it a question from that story at the bottom. So the first thing we need to do is grab an embedding model. It's able to download that itself if you don't already have it. So if you're running this the first time, that step will take a little while because it's a little big. Then we're going to pull up our Llama Index OLlama class, which comes with the Llama Index libraries, and initialize an LLM client there using a temperature of 0 again, like we did in the last demo. And then in this just one line, vector store index from documents, it's going to do all that stuff we did in the other demo with chunking and retrieving and storing it in the vector database. This is pretty much all we have to do to build that data store. And then here, we're going to say, give me a query engine interface to that index. It's possible using Llama Index to say as chat client or something. There's a couple different variations and modalities you can use to interact with it. But here we're going to ask it to act as a query engine. And we're going to ask it, what was Frankenstein's monster's real name? Which, of course, is a trick question, but we'll see. Hopefully it won't respond to Harold. And it's reading the book really fast right now, and it got it right. The text does not provide any explicit mention of a name given to the monster by Frankenstein himself. The monster refers to himself as a demon and a wretch, but these are not names. That was less than 20 lines of code, and half of those were blank, so not a lot of code to use. If you're building a RAG type system, I would definitely look at Llama Index to put it together. To prepare data for research augmented generation usage, I've had some luck following these steps. If you can prepare your source documents, it'll be helpful, ensuring that all tables and graphs have textual descriptions, since it won't deal with that very well. Ensuring that the text is clear and straightforward as possible. A fact document is probably the most suitable, so anything like a question and answer format works fairly well. Split the document into smaller chunks, overlapping text if you need to break in the middle of a topic. Convert the chunks into tokenized embeddings and then store those in a vector database, which can be anything from a temporary RAM-based store to an Elasticsearch cluster or other specialized vector database. Then when it comes time to ask it a question, tokenize the question and use that to search to the vector database. And then include that and the response, the result of the search, in the prompt to the LLM. And the more I prepare the source documents to look like a FAQ in Q&A format, the better results I've gotten. But I've also had to pause and ask myself whether this was delivering better value than just doing a search of the source data myself and looking at the results. To be honest, I don't think it is in many or even most cases. Even with all this preparation, the response may still contain factual errors. The impact of these potential errors is going to be dependent on what you do with it. Moving on to a twist on LLMs, we're going to look at a multimodal model. It's a large language model connected with a vision encoder that allows the model to describe and interpret images. I'm not going to get into too many specifics about how that process works because I'd embarrass myself, because I just discovered the model I'm going to use here, named Lava, was co-developed by UW-Madison grad student named Liu Haoshen. So, great work, dude. Really, really happy with this. Impressed. All right. So the first one we're going to do with this is we're going to give it images and then ask it questions about the images. We're going to have two different models at play here. First of all, there's a very, I'm going to call it a short model called a blip captioner. I think they've been around a bit longer. This one is developed by Salesforce. It just provides a short generic description of what is portrayed in the image. And then we're going to contrast that with the interpretation of the Lava model that combines a vision encoder with a large language model. You'll see that the Lava model includes and interprets much more detail than the simpler blip model. It also provides things like emotional context from the image. You can ask it questions about things in the image, and it will attempt to interpret the picture to answer them. For this demo, we're just going to give it one image or two at a time and have both the blip model and Lava describe them to us. Okay, so a demo of a multimodal model called Lava. Now we're also going to run the image through more of a conventional vision encoder, a blip processor, which is used for captioning images, often to train other types of models. That's what we're doing at the top here. We're just preparing the blip model. That's the Salesforce one I mentioned. That's going to run locally here in Python. We're not going to have Ollama do it. It's not as resource intensive to do, and it doesn't need a whole LLM setup to do it. We have a function to encode an image to base 64. That's how we send the image to the model. And then here, this is what's called every time the user hits return. The encode image function will get the image that the user gave us and the prompt they have for the image. And then we're going to first run it through the blip captioner to get the blip caption quickly. It'll be short, usually less than 15-20 words. Even if we tell it can use 40, they're usually a lot shorter than that. Then we're going to push that to the screen. And then here, we're going to use the Ollama interface to send the image and our prompt to the large language model, to the Lava model with streaming on. And we're going to force that to the screen then as we get lines back. And then we're done. Here, this stuff at the bottom is just setting up the interface. We're doing it a slightly different way than the other one, just because it's a more complex interface. So let's get that running. And already in the virtual environment, already installed everything. We're ready to go. And let's see here. Refresh that. Here we go. There's the interface. We're going to set the image. Let's start with that. It's a dog. And then down here, we're going to just say, please describe this image. See what we get with that. And all right, it's going to send it. Got the blip model back already. A large golden retriever sitting down and looking at the camera. That's true enough. And then here we're getting the results back quite long in the image. There's a light brown Labrador retriever. You see, we get a lot more detail here. It says the dog appears to be in good health, fur looking well groomed. It's giving us the pose. Talks about the background. So it's really a richer interpretation of the image than just, a dog sitting there looking at the camera. So let's try another one. It got the dog right. So let's try something a little different. Okay. What I'd like to do is, what model of car is shown in the image? Let's see what kind of gearhead it is. What year and model of car? I mean, it's a classic car. There's probably a zillion images of it on the internet. Let's see if it gets it right. Well, the blip model got it right. It knows it's a Corvette. So let's see. Oh my. No, it doesn't really know cars. It thinks it's a Mustang. That's, if it wasn't ever trained on cars, it's not going to go. It's going to know what a car is. It might know some things about it, but no, it thinks it's a Ford. Oh, that's sorry, Corvette owners. Let's try something else. Let's see if it knows what a jackalope is. All right, so what sort of animal is shown? Yeah, no, blip doesn't know what a jackalope is. Okay, no, it doesn't know what a jackalope is, but it does know that it's a faked picture. It's an AI picture, so at least it's got that. Secondly, one of the interesting things, or thirdly, you can do with this is have it describe things. Could say, are there any hazards, any possible hazards shown in the image? And I haven't tried this yet with this image, so we'll see what it says. Blip model is just going to interpret it again. I didn't ask it to do anything differently. And that's about all it can do. Well, it thinks it's safe. So I've seen other pictures, it'll mention traffic or water or something like that, but it seems to think this one's safe. So that's how one can use this. I can think of a lot of uses for this technology. Even the blip captioning, to be honest, I sometimes take a lot of screenshots. I'll have 400 of them on my desktop. I don't want to look through them all. They all have the same names, basically. So maybe something that ran through them all and named them all according to what was in them would be kind of cool. But it's another way to use this technology. So this demo pushes the Lava model to its limit and past its limit. We're going to try to get it to interpret an XKCD cartoon, hopefully reading the text as well, and then ask it to explain the joke. It's asking a lot, from understanding the cartoon drawing and captions to understanding Randall Munro's sense of humor, and it doesn't get it right very often. But it's illuminating to see it try. When it does get the answer wrong, take note of how sure of itself the LLM seems to be, like all LLMs. And once the explanation it's generating gets going in a certain direction, it just keeps going in that direction. For the last demo, we're going to put that vision encoder LLM Lava through its paces by giving it a random XKCD cartoon and asking it to interpret the answer. Now that's going to be a bit of a lift for it because if you're not familiar with XKCD, it's a comic made by a physicist that used to work for NASA before he was a comic strip artist. And they tend to be sometimes cerebral, sometimes very obscure. And I can't think of things that are much harder for something to interpret than a Randall Munro cartoon. So let's see what it can do. First, in the example here, we're just going to grab a random cartoon. That's what all this stuff is for. In the code, if you pull this down and run it, you can give it a number and have it interpret a specific cartoon as well. So we're going to pull that down and start to build a response header to show on the screen here. And down here we're going to end up with the image from the cartoon and draw that right away along with the header and the alt text. And then we're going to send it all to Ollama to have Lava interpret it. So we're going to have it say, briefly explain the humor in this comic. The alt text is, and then give it the alt text because sometimes that's part of the joke. In this API call, it'll take care of base64 encoding the image itself. So we just give it the raw Python PIL format image. Tell it to stream, and options, we're going to say 0 temperature. Although this one doesn't do badly with a higher temperature, it sometimes really goes off the rails with that. And then, yeah, it's just going to keep painting the response on screen, one word at a time, until it's done. And let's try this demo out and see what it does. Already have my virtual environment set up, so get that running. And go back here, bring up the new app, and all I'm going to do is click generate. It'll pull the new cartoon down. And let's see, Rob, you look terrified. What's wrong? Remember last week when we dug up all those Indian bones, made puppets out of them? It turned out they were buried over an ancient Indian burial ground. Okay. So what it's saying, it's interpreted this as the humor comes from a juxtaposition of a typical school setting with an unexpected and absurd twist. They're depicted as students, but instead of engaging in normal classroom activities, they're shown to be involved in criminal acts such as smashing up a voodoo shop, which was in the alt text, and digging up bones. So it did pick up bones from the caption. I don't know why it thinks they're a student. Final panel shows a character saying we've made a huge mistake, which it doesn't actually say. It does that. And yeah, then it tends to moralize. By engaging in criminal activities, they're also expressing remorse for their actions. So that's how it does on that. Sometimes it does better, sometimes it does worse. It is interesting to see what it picks up and what it ignores and where it goes with that. But anyway, now you've got this code to play with, and you can try it out yourself. There are coding assistance type LLMs available that you can run locally on your machine as well. CodeLlama was released by Meta and seems to be one of the better ones. I would warn that there's emerging evidence that widespread use of LLM-generated code is not helping our industry's technical debts. Coding LLMs have all the same reality problems as other LLM from any other type, and the code it generates might work, but it might not be the best way to do something. It won't consider larger architectural concerns, and it only knows as much about your project as you include in your request to it. Some might say it can do as well as a new intern, but unlike the intern, the LLM will never learn from its mistakes, and it will never improve, so you need to check on its work on an ongoing basis. They will make stuff up, even ChatGPT, fake class names, non-existent functions, and misunderstood assumptions about what some code is supposed to do. That being said, there are freely available plugins to use a coding assistance model with Ollama and other platforms from within JetBrains IDEs and Visual Studio Code. They all use the OpenAI compatible API that Ollama provides. So, a few conclusions. I'm not too worried about a John Henry situation between me and an LLM at this point. LLMs don't really know things. They predict likely answers. Retrieval augmented generation can be useful, but is it useful enough? Is it better than searching a knowledge base if you can phrase your questions using natural language like with Google.com? Large language models have been experiencing a lot of big hype this last year, and everyone is adding them to every possible product, not because they're appropriate or useful applications of technology, but because it's a marketing point. I heard someone trying to teach one to drive a car the other day, which terrified me. LLMs are not a universal AI toolkit, and they are not appropriate to use for every task. That's why I'm hoping you can take the code and the explanations in this presentations and try them out yourselves. Try them out in your own use cases and decide whether they add value or not before you commit a lot of resources to finding out. And here's some resources describing the things I've been talking about. And if you have any questions, just drop me an email at brian.hill@wisc.edu. And thank you for your time.